Well, first of all, we're happy that Laurens is willing to be here and present his work. So I want to say a little bit of his background. So he studied at the Free University and then did a PhD in Armholt on experimental physics, of course. He did a postdoc first in Paris, and then came back to Armholt and ultimately made his career in Delft University, where he first was an Anthony van Leeuwenhoek professorship, so that's one of the awards that he got, and ultimately he became the professor in optoelectronic materials. The Anthony van Leeuwenhoek professor, that is one award, but he has also won a Vici grant and a Young Scientist grant and a top grant, so he is well connected in the Netherlands, and so we're very happy that he is here and can tell us about his latest work on basically a collection of properties of excitons in semiconductor materials. That's a short.
Yeah.
So please go ahead, Raoul.
Okay, thank you very much, Henk, for the introduction, and also to you and Michael for having me today. It's a pleasure to present something about my work, and that was work done in close collaboration with Henk and with Daniel and some other people that I will mention. Okay, so we are working on quantum dots, small spherical or almost spherical particles with a size of a few nanometers. Elongated nanorods of semiconductors. I've done a little bit of work on perovskites, and I'm working on two-dimensional materials like transition metal dichalcogenides. I want to work on covalent organic or metal organic frameworks where you can make stacks of aromatic molecules like benzene rings closely stacked that form paths for energy or charge transfer. I'm thinking about going into topological insulators together with Henk. We have just been discussing about it. We did so several times, and I hope it's going to work out. And I've been working also on exciton and charge transfer between different layers in hetero junctions for solar cells. For instance, an organic layer where you photoexcite a molecule, and then the exciton can move into another metal or inject either an electron or a hole in the other material. Okay, why do we do this? Well, with an eye on eventual applications. For instance, these materials that I've just mentioned can be used to process from solution. You can tune their band gap by change of the chemical composition or the nanostructure, and then from solution you can do reel-to-reel printing and cover large areas of the materials, and in the end you can hopefully make light-emitting diodes and solar cells that are cheap and flexible. So what are the processes happening in, for instance, a light-emitting diode? In a light-emitting diode, you inject electrons from one electrode, holes from the other electrodes, and then the electrons and the holes are supposed to move close towards each other, form an exciton, and then the exciton is supposed to decay by the emission of light. The reverse is what happens in a photovoltaic cell. Then sunlight is coming in, and it could be that you directly form free charge carriers. That is what happens in a conventional silicon solar cell. But if you make a solar cell out of organic materials or quantum dots, you usually have first an exciton in which the electron and the hole are bound together, and then the exciton is supposed to move towards, in this example, an electron accepting layer, where the electron jumps into the other material component, so that you get an electron and a hole that can separate from each other, move away, and contribute to the photocurrent of the photovoltaic cell. Now, in my group, we are not making devices, we are doing spectroscopy. And we are doing time-resolved spectroscopy. So what does it mean? We take a material and we come in with a laser pulse with certain photon energy, and this pulse has a duration typically of 100 femtoseconds, or it can be longer in some cases where it has a duration of a nanosecond. And then we look as a function of time what happens with these species. So during time we look at the motion of excitons and charge carriers, their mobility, but we also look at their spatial extent indirectly, for instance via the polarizability of excitons. We look at the decay of these species by trapping and defects, or the recombination of free electrons and holes into excitons, and then the subsequent recombination of the electron and the hole either via light emission or a non-radiative process. And we also look at annihilation of excitons. So when two excitons get close together, then one exciton can transfer its energy to the other exciton, and you lose one exciton, and that's so-called Auger recombination. And we study these processes experimentally by optical detection, microwave conductivity detection, and terahertz conductivity detection. And I'll tell you later about these techniques that we use to study the excitons and charges in the nanoplatelets. They've always been doing some theory, electronic structure calculation, scale of P, time-dependent DFT, and I did a little bit on GWBSE. We have been doing Monte Carlo simulations, computer simulations of the hopping, for instance, of charges and excitons and their mutual reactions. And we have been doing for a couple of years already analytical and numerical theory with Henk Stoof here from Utrecht. Now, what the questions are that I will also address in this talk is, for instance, if you pump with a certain photon, you can have a low energy, let's say a red photon, or a high energy blue photon. What do you make? These bound excitons or free charges, and how do they relax? What do you get? And what do you get if you come in with a delayed propulse? Do you get excitons and you induce emission, stimulated emission, like in a laser from the excitons? Or do you produce the next exciton close to the exciton left after the pump pulse, and you form a bi-exciton, a sort of hydrogen molecule of 2 holes and 2 electrons instead of 2 protons and 2 electrons? Or do you form a trion species? It's like an H- atom, so you have a hole, an electron, and a second electron. And things that we study is, for instance, singlet fission in organic materials. When you photoexcite a molecule like terahertz, with light you can promote an electron from the highest occupied electron to the lowest unoccupied electron. And a photon cannot change the spin of an electron. So initially the spins are opposite. So you have a singlet state. But then you can also have a triplet state in which the spins are having the same direction. And triplet states have a lower energy because the spins cannot, the electrons with the like spins cannot be on top of each other according to the Pauli principle. So they are, let's say, relatively further away from each other. So there is less Coulomb repulsion. And if you get a singlet fission process, you have 2 triplets. And if you then get charge transfer to a semiconductor, you can produce 2 electrons and 2 holes out of a single photon. And that can enhance the efficiency of a solar cell because you double the current. And we also studied this a lot. A large part of my work in the last 10 years was on carrier multiplication in semiconductor quantum dots and also in tin 2D materials. And recently also in bulk materials in transition metal diisocogenides, where we promote an electron from the valence band of a material to the conduction band. And then usually what happens, for instance, in silicon is that the excess energy, the difference of the energy between the photon and the band gap, is lost in the form of heat, just by electron phonon scattering. And then the efficiency of a solar cell is lower than what you would achieve if this energetic electron would scatter on another electron that is still in the valence band and promotes that next electron to the conduction band. Then also you can double the current of the solar cell. And in case you have a conventional solar cell, then at 1 times the band gap, this is the photon energy expressed in terms of the band gap, and this is the quantum yield. So if you produce 1 electron hole pair after having a photon energy of the band gap and it remains 1, then you get this power conversion efficiency curve for the solar cell. This is now the band gap of the semiconductor, and this is the power conversion efficiency. And you see that then the maximum is about 33%. For an ideal band gap close to, I think, 1.3 eV. If you now would have this carrier multiplication or singlet fission, and if it's the highest efficiency that you could achieve, so at twice the band gap you have a quantum yield of 200%, and you go to 300%, so if this staircase kind of behavior, then you can enhance the efficiency to about 44%. And economically, that is very important. Intuitively, you would say, well, 33, 44 doesn't matter so much. That's what I thought, but people have told me that technologically and economically, that is really an important step forward. Okay, this is sort of general overview of the things that I've been doing and still doing, but in this talk, I'm going to focus on the behavior of photogenerated excitons and charges in cadmium selenide nanoplatelets. So that's the work that I've been doing with Henk and Daniel. So what are these nanoplatelets? So this is a sketch of it. That's like a rectangular material with a certain thickness. The thickness in our case is 1.4 nanometer. There's 4.5 cat selenide layers. So it's 4 times cadmium and 5 times selenium. And they have lateral dimensions of 10 to 35 nanometer, and in the other direction 5 to 15 nanometer. And here you see a transmission electron microscopy image of these nanoplatelets. And they are not entirely rectangular, but close to rectangular. And they are passivated with organic molecules with a low dielectric constant, and that passivates the dangling bonds on the surface and makes it possible to dissolve these materials in common organic solvents like hexane. And we also got some samples from people in Belgium, from the University of Ghent, Pieter Geijerkap and Zeger Hens. I'll show you some results from platelets I got from them, but that's already a long time ago. Okay, I'm going to cover 3 topics. First of all, I'm going to show you how an exciton moves, or how we derive that from steady-state optical absorption and photoluminescence spectra. And according to the interpretation of these experimental data, you can envisage the exciton as being a small particle that moves like a particle in a box between the edges of the nanoplatelet. Then we are going to look what happens if you photoexcite these cadmium selenide nanoplatelets with different photon energies. You get electron hole pairs, excitons, how they relax, how long that takes. I can already tell you it's pretty fast, it's within a picosecond. And then if you come in with the second pulse, it's some delay time after the pump pulse, what do you produce? Now, these species, but I will get into that later on. And then we also worked on situations in which you have a high intensity of the pump laser pulse, where you put in many photons in one nanoplatelet, so that it's completely filled with excitons. And then you could expect that you get a sort of metal, that the electrons don't know to which hole they belong anymore, and that you get an electron hole plasma. Now, according to theoretical modeling together with Henk, the excitons are, well, and observations, the excitons remain stable, even in case they are just sitting close together. We couldn't go to an even higher density because of the limitations of our laser power. Okay, topic number 1, the particle in a box motion of the excitons. So here we have a nanoplatelet with lateral dimensions Lx or y, and these lateral dimensions, they are tens of nanometers, they are way larger than the exciton bore radius of 1.2 nanometer of an exciton in cat selenide nanoplatelets. And the lateral motion is just confined by the lateral sizes. If you had an infinite quantum, well, the excitons would move like free particles. So what we do is we absorb a photon and we make an exciton, and we can look at the absorption as a function of photon energy. But you can also look at the photoluminescence decay. Once you have an exciton, you make it at some energy, it will relax to the lowest energy state roughly. There will be a few excited states populated due to the thermal distribution of particles, and you can look then at the fluorescence. Now, let's first look at the optical absorption spectrum. So what we do is we dissolve these nanocrystals, nanosheets in a liquid. I think it was hexane, and it's yellow, whereas bulk cat selenide is black. And it's yellow because the quantum confinement in the thickness in the LZ direction, the direction perpendicular to the sheet, the plane of the sheet, causes the exciton to be, let's say, compressed, because in the bulk the exciton bore radius is 5.4 nanometer, and these nanoplatelets are only 1.4 nanometer. So you get quantum confinement effects, and that increases the band gap. And now the absorption as a function of the photon energy looks like this. You have a so-called heavy hole exciton. That is the upper valence band. You have a hole in the upper valence band, and then let's say an electron in the conduction band, and they attract each other and form the exciton. Then there's also another exciton at somewhat higher energy. That's the light hole exciton. That is the next valence band that lies just below the upper valence band. And then there are continua in which you excite electrons and holes that move in an uncorrelated way. So in a diagram, it's a little bit like this. You have this heavy hole band, a light hole band, and a conduction band. And then you could say combine a hole in the heavy hole band with an electron and you form a heavy hole exciton. And you can also say combine a hole from the light hole band with an electron and I get a light hole exciton. So as I said, the thickness of these nanosheets, LZ, was 1.4 nanometer. That's way less than the exciton Bohr radius, which is 5.4 nanometers in blue. So you get, let's say, complete in situ, complete squeezing in of the exciton. It's almost a 2D exciton, 2D hydrogen atom. And the energies, due to that confinement, can to a good approximation be described by this expression. That is just a particle in a box expression. And for n is 1, for an electron, as it's pi squared h bar squared times n squared, which is 1 over 2 Lz squared, and then divided by the effective mass of the electron, and same for the hole. Now this causes the cat selenide nanoplatelets to be yellow and to have much higher band gap than bulk cat selenide, which is black. And then the Bohr radius was 1.2 nanometer. Of the excitons, you could say the diameter is about 2.4 nanometer. Now, if this is tens of nanometer, then the exciton is much smaller than the lateral dimensions of these nanosheets. Okay, now Daniel gave us different samples that we studied by optical absorption spectroscopy, the steady state. For instance, he gave us samples where Lx, that is in the long direction, is 29 nanometer, and in the width was about 5.4 nanometer. We measured the optical absorption spectrum, that is this solid line, and the photoluminescence spectrum, the dashed line. So far, so good, nothing special. But then we went on to the next sample, which is a little bit wider. It's also a little bit less long. And what you see is that now these peaks have shifted to the red, to a lower energy. And that can be qualitatively understood by the fact that this dimension has become larger. The quantum confinement in the direction is not so important, also plays a role. I said to cause it a little bit to go up. But this is winning, going from 5.4 to 6.4 in the width. It reduces the energy. And then you can make the next step, so you go to 8, so now this is almost staying the same, so you go from 6 to 8, and you see you go a little bit further to the red. And then they are almost square, 13 times 13, and then you see they're even further to the red. Now that we described by using the simple particle in the box model at the first year quantum mechanics course, where you have quantum states, n1, 2, 3, 4, typical wave functions, sinus n pi x over the length. The energy is given by this. And there's the 1 over the length squared. And now we have a two-dimensional system, so we have an x and an y, which can both be 1, so you have no nodes, and then you can have in the x direction, and x is 2, so you get 1 node, or in the y direction, or you can have both quantum numbers equal to 2, so you get 2 nodal planes. And the wave function is just simply the wave function for the motion in the x direction and the motion in the y direction. Now, then we started to analyze the photoluminescence spectra, because that is, let's say, in a way the easiest, where most of the excitons have relaxed to the lowest nx and y states. These are the spectra that we got. And you can see here, this is the red line is going here through the top of the photoluminescence spectrum of the nanoplatelets with the shortest width. And then if you make the width wider, it was shifting to the red, to lower energies. And now what we took into account is that you have a Boltzmann population of the center of mass motion states with these energies, simply the particle in box states. We have these particle in box wave functions. Then with these wave functions you can calculate the oscillator strength for excitation from the ground state to different excited states with different nx and ny quantum numbers. And the dimensions appear here. And then if we take this all into account, we take a Lorentzian line shape for the excitation to the different quantum states with a width that includes exciton-phonon interactions. So the width is increasing with detuning because you need more and more phonons if you emit a photon that's further away from the resonance. There was a Gaussian distribution of the sizes that we determined from TEM measurements, and there's also some structural disorder that we put in phenomenologically. And then if we do that, we get from the fit this black curve that is completely on top or almost completely on top of the experimental spectrum. I switched a little bit. Something wrong from the photo. Oh, sorry, this is the photoluminescence. The fit here is now shown by black lines. You can see they now are almost on completely on top of the experimental lines, and then you have contributions of the different quantum states, the different X and Y values, to the photoluminescence spectrum. And you see here that this sort of orange colored dashed line is almost falling completely on top of the photoluminescence curve, and here as well. So it means that in the photoluminescence is almost entirely from the lowest energetic state. Yeah, because the next state is higher in energy and higher than KT and is less populated. So that's the photoluminescence. Now we go to the absorption, and so we have this transition to the heavy hole, the light hole, exciton, and the continua. If you do that, we get this black line for the absorption intensity as a function of the photon energy, and then you can see that the first absorption peak that is due to the NX and Y is 1, and then you get the second plus the other the NX is 1 and Y is 3, etc. The quantum numbers are odd because according to the selection rules, a transition from the ground state to an even quantum number for the particle in the box is optically forbidden. So this is now the heavy hole peak with all the center of mass motion states taken into account. This is the light hole peak that contributes to this one, so it's superimposed on the calculated blue curve, and then we have two continua. And from this we had adjustable parameters that are the exciton binding energies of the heavy hole exciton, so that is the energy of the heavy hole exciton without translational energy with respect to the continuum. That was 135 millielectron volt, and for the light hole, that is, let's say roughly from the top here to that one, it is about 300 millielectron volts. That were adjustable parameters. In addition to a Gaussian disorder, a width that brings into account a disorder in these nanoplatelets due to size distribution, due to inhomogeneities, and so on. So I think this simple particle in box model can amazingly well describe the experimental data. Now I think I will skip this. So to conclude, the first part of this talk is that the exciton center of mass motion can in these nanoplatelets be well described just by a simple particle in box model. And this we published together with Henk in 2020.
Can I ask a question? How long does this exciton actually live?
Oh, nanoseconds, several nanoseconds. Yeah.
That's it. Just to get an idea of this time scale, let's say during the several nanoseconds, how often does it bounce back and forth?
That I didn't calculate that. We can calculate it. Yeah. I don't know by heart. I didn't ask me that, but you can of course calculate.
For this approach to develop, it should bounce back and forth. Let's say a long time. I would say before decaying. Otherwise.
Yes. Yeah. Which it does because the energy, if you calculate the quantum confinement energy, is tens of millielectron volts. So no, I don't know by heart how that translates to a velocity, but you can do it afterwards if you want. Yeah, but the way I see it is it's simply a coherent state, completely delocalized in this box.
Mm-hmm.
And then
I also have a question about the exciton. So I'm a bit surprised by, so you're using the particle in the box twice, right? Once for the Z direction and then once for the 2D part, right? And
yeah.
For the Z direction, I'm a bit surprised that it works because somehow the size of the exciton is larger than the Z direction itself. Like, how can it even work bigger?
In 3D, it's larger. So if I have no quantum confinement, if I have a bulk material, then I have an exciton bore radius of, let's say, roughly 5 nanometer. Now I make the material thinner, 1.4 nanometer, so I get a potential barrier because outside the nanoplatelet the energy of the electron in the hole is much higher because we have a hexane solvent. Yeah? So I squeeze, let's say, physically the exciton into this small, let's say, width or thickness, and because thickness of 1.4 nanometer. So both the electron and the hole are now confined, and that confinement energy, that determines all the properties. There is, of course, a Coulomb energy as well there, but that is, let's say, taken into account in the original band gap, and on top of that you get the original interaction, which is then enhanced by the fact that the dielectric constant of the environment is lower, plus the extra kinetic energy that you get due to the confinement in the direction of the width. Maybe that's not.
Okay, do I understand correctly then that instead of, so in the bulk materials you would have like a 3D exciton where you have the more massive hole, roughly speaking, at the center, and then the electron is circling around it in like spherically, and now you confine it so it's just basically a 2D version of the 3D.
Exactly, yeah.
Okay.
So in the Z direction you have electron and hole confinement, and in the XY dimension you really have the boson part.
Yes, yeah, exactly.
That's the point.
But you are still assuming a spherically symmetric exciton, right? That's where your 1.2 or radius for the 2D exciton comes from. It's roughly the thickness of your.
Yeah. It's like let's say it's not spherically. It's like a plate, a round plate. The exciton, it's a 2D exciton in the XY direction. In the plane of the nanoplatelet, we assume it's like a circle.
Okay, but then you
Disc, yeah, it's a disc. I couldn't find the word.
Yeah.
The disc.
But then you're taking into account then the dielectric function perceived by the electron hole pair is modified by the fact that you have a lot of dielectric material.
Well, that determines the final binding energy.
That determines the high binding energy that you measure in the end.
Yes, yeah. The low dielectric constant of the medium enhances the exciton binding energy.
If spherical, they would actually have to probe the low dielectric constant part of the field, and that is cannot do it, so it just squeezes into the.
Even if you only squeeze it in, if you don't change the dielectric constant, if the dielectric constant is the same, and if you go from a 3D exciton to a 2D exciton, the binding energy increases by a factor of 4, theoretically.
Okay, yeah, but yeah.
And then on top of that, you have changes in the dielectric constant that gets lower in this case, could also be higher, it depends on what you put around the nanoplatelet. And then the factor 4 due to the 2D confinement is a little bit less in our case because it's not infinitely thin, but it still has a finite thickness.
But what you see as the binding energies is like it's one order of magnitude larger than it would be for.
No, I think in bulk, yeah.
In the bulk is very tiny.
It's tense. So it's less than an order of magnitude. I think it was 16 in bulk.
Yeah.
We find 130, so it's 8 times or so.
As you are busy, can I ask a question? Why is for the light electron hole the binding energy so much bigger than for the heavy electron hole?
Because the light, it's mainly the continuum for the light hole is lying much further, and we count it from the continuum.
Yeah, okay.
The light hole band is already lying deeper.
Yeah.
We count from the continuum. If you would count from the vacuum, it would
But
be
so
different.
relatively it's much more squeezed by the electron hole attraction than for the heavy hole. With respect to the free particles.
Yes, with respect to the free particles, yes, yeah.
While we were discussing about the size, one question before you run off from this. So you were talking about like the lateral confinement and the vertical, or maybe vice versa. Does the size in in the plane matter? Does it actually depend on how much you confine it? Like, should I think about, let's say, a ball and you squeeze it, it keeps roughly the same? Or should I think about putty, as you press it, it just flows out?
Yeah, the thinner you make them, the more they will be confined.
Okay. So they will also become smaller in
Yes.
Okay.
Yeah, is that right? Yeah.
Yeah,
Yeah,
you
yeah,
increase the binding energy.
yeah.
Putting it.
The thinner, the higher the exciton binding energy, and the smaller the size of the exciton.
So it's not a drop of water that you confine, it's the opposite.
No, exactly. That would go the opposite. Exactly. Yeah. Yeah. And follow-up experiments would be to change the thickness, really. Because then we need people. Okay. The second topic, that is the most recent thing actually that we did with Daniel and Henk, that is the photogeneration and ultra-fast relaxation dynamics of excitons and charge pairs. So we came in with laser pulses with different colors, different photon energies with a duration of about 180 femtoseconds. Then we looked at the thermal relaxation. We claimed to have done it about 1 picosecond. And then we come in with probe pulses to see what is left after the relaxation and what you produce with the probe pulse. And these nanoplatelets were having a size of 25 times 8 nanometers. Okay, so going back to this optical absorption spectrum, steady-state spectrum, we had here a peak due to heavy holes, a peak due to light holes, and then a continuum. So we photoexcited at the heavy hole peaks with the idea that initially we make excitons. Then we went to the light hole peak, not shown here in green, but then you produce predominantly light hole excitons, and then we went to the continuum where you produce free charges, uncorrelated electron hole pairs. And once you've done this and you have done this relaxation, the following things can happen. If you come in with a probe photon, depending on the color, you could, for instance, be resonant with the exciton energy and induce stimulated emission of photons, like what you do in a laser. You have an excited state, you come in with a photon, and you get 2 photons out. Could also be that the probe photon produces another exciton close to an already existing exciton left after the laser pulse. Then you form a bi-exciton. It's a little bit lower energy. And you can also produce a trion if you produce the exciton with the probe photon next to a charge left after the pump pulse. Now, what does the experiment look like? Again, a QuMat with a solution of nanoplatelets. You come in with a pump pulse that photoexcites the nanoplatelets, so it makes excitons and charges depending on the wavelength. And then with some delay time, we come in with a probe pulse. And this probe pulse consists of many colors. It's a so-called white light probe pulse. And we can distinguish at which colors you get absorption or emission. I will show you that, but suppose you were taking the color of the photons, just agreeing with the energy, the photon energy of the heavy hole exciton, then you could get a stimulated emission. So the photon comes in, it, let's say, pushes the electron down into the hole state, and then you get 2 photons out. So you get more light on your detector after the pump pulse than before the pump pulse. So what do the spectra now look like? So if we pump at the heavy hole exciton energy, where you initially produce mainly the heavy hole excitons, then you get this spectrum. So in black here is the steady state absorption spectrum, but plotted on that is now the absorption spectrum after we have photoexcited the electron with the pump pulse. And this is with a time resolution of about 200 femtoseconds. That is due to the duration of our laser pulse. Now what you see is that instead of having this peak, you see there are 2 little bumps here, and there's a lower absorption. Here there's a little bit of higher absorption, here there's a little bit of lower absorption. If you take the difference of the spectrum after the excitation, so that's A on minus the steady state spectrum, and there was no pump pulse, you get this shape of the different spectrum. So you really see that you change the spectrum after pumping. And if you now analyze the data, we did that by taking for the A0 spectrum everything with the parameters that we got, of course, from the previous work that I showed you, but also after the pump excitation, we shifted a little bit in energy due to filling of traps, but that's a detail. But then we added to it a Gaussian, that is this yellow curve, due to the formation of, for instance, these bi-excitons and trions. And here there's something about light hole excitons, and here about free charges. I have a few more slides after that, and we'll go into that more deeply. Then if we excite with a light hole energy, it's a little bit more energy, you see that the contributions of these three curves are different. For instance, what's striking is that here you have a negative blue peak that is due to stimulated emission that is much smaller if you excite initially at higher energy, when you don't initially produce heavy hole excitons. There is some stimulated emission. That means that within the 200 femtoseconds, part of the initially high energy electrons and holes have already recombined to form the heavy hole exciton. Okay, let's go step by step. So this blue negative bleach peak that is due to emission of from an exciton, so the probe photon comes in and produces another probe photon. And that you see, as I just said, is the most, is the most important if you excite at the exciton level. But it also occurs already at the higher excitation energy, so we can conclude that some electrons and holes have already relaxed. If you look at these yellow curves, there is an induced absorption, so more absorption after you have produced the excitons and the holes, and we think that is due to the fact that the pump produced one exciton, and then with the delayed probe pulse, delayed by 200 femtoseconds, you produce the second exciton next to the already existing exciton. And that has a little bit of a lower energy, but this is a bi-exciton. There is a binding between the two excitons. And then it could also be that you form trions, that you have charges left from the pump pulse, and then the next exciton from the probe pulse is produced close to a charge, and you get a trion with a somewhat lower energy than the exciton. Now, and then you can also, we also observed a little bit of absorption here at the higher energy, so that is between the energy of the heavy hole and the light hole exciton. And what I can imagine is that what happens, you have a heavy hole exciton already present, but now you produce with your second photon a complex of a light hole exciton and a heavy hole exciton. So it's a light hole, heavy hole bi-exciton, which has an energy lower than the light hole exciton, but above that of the heavy hole exciton. It could also be that you form a light hole trion, so you have a charge and you produce a light hole exciton close to the charge left after the pump pulse. Now then the continua, if you are sitting here in the continua, you are producing electrons and holes, let's say in the conduction and the valence band. Once you have that, you get Pauli blocking. So if a state in the conduction band is occupied by an electron already, shown here, you can no longer photoexcite from the valence bands to that electron state. Also if you have a hole, and if you have an electron in the conduction band and a hole in the valence band with the same momentum, quasi momentum K, you can get stimulated emission. So that can give rise to this bleach here, and that the absorption is effectively less than in the ground state. Now then about the relaxation, if you look at these transient spectra, so the different spectra of the pump on and pump off, at a very short time, if we pump at different energies, at red, at the heavy hole energy, the light hole energy, or the continuum energy, you get the curves with the three different colors, you see that if the pump and probe pulses overlap, that's called T is 0 picoseconds, the shape of these spectra is really different. They get relaxation because the amount of excitons, free charges and so on is equilibrating, and then I would say after a picosecond the spectra are merely the same. So after a picosecond everything has come to an equilibrium, and that equilibrium is achieved by electron phonon scattering, release and absorption of phonons. So conclusion 2 of part 2 is that the photo-generated excitons, electrons and holes equilibrate within a picosecond, and the probe photons can do all these three processes that I mentioned before. Yeah? And any questions? No?
I have a question. So this image talks about one single nanoplatelet, but you're of course measuring an ensemble of nanoplates. How do you know it's a bi-exciton and not an exciton in a nanoplatelet that is already decayed and has no excitons to leave?
That doesn't cause a change in the absorption. So first of all, if you come in with a pump photon, you don't photoexcite all nanoplatelets. So if there's a nanoplatelet that's not excited, then with the probe photon, I see the same thing without the pump as with the pump. So that gives a 0. If there was an exciton in a nanoplatelet that had really decayed back to the ground state, and if then I come with the probe photon, after a long time I also see no difference. So then the difference is 0. Yeah, that makes sense. Yeah. In the meantime, this paper has come out. Yeah. Okay. Now then the question that we ask ourselves is, do excitons survive at a high density? So if I pump really hard, if I photoexcite it and we did it close to 60 photons per nanoplatelet, then a nanoplatelet is more completely filled, sketched here schematically. Are the excitons still existing as correlated electron hole pairs? So let's say an electron knows to which hole it belongs, or do you get an electron hole plasma like in metal? The answer is you get the upper one. I can already tell you that. So we made excitons and charges with photons, and we wondered what is the effect of the density, and we brought into account the equilibria. Together against Stoffel, we worked out with the PhD student the equilibrium between the free electrons and holes and the excitons as a function of density. This we did with terahertz spectroscopy. It's a bit of a funny technique, but what you do is you can make a terahertz pulse, and that's an electric field with more or less a single cycle. Yeah? I can tell you how we do it, but it's not so relevant at the moment. This has a duration of about a picosecond from the beginning until the end. And if you have a sample without charges, then the terahertz pulse goes through. It is delayed a little bit due to the dielectric constant of the medium, but you get something with merely the same shape. Then you come in with an optical pump, and then you make free charges and maybe excitons. And then if the terahertz pulse goes through your sample, then what will happen if you have free charges, the amplitude will decrease because the terahertz radiation can sweep up the motion of the electrons and the holes a little bit, so it transfers energy to the charges, so let's say the power must decrease, so the amplitude of the terahertz fields will decrease. But then also due to charges and due to excitons, you get a phase lag because you change the dielectric constant, or the speed of light in the material, and that gives a phase lag. So you get a reduced amplitude and a phase lag, and that we can measure. Now the real conductivity, as we call it, due to free charges, that gives you the reduction in the amplitude. So the conductivity that we get out of these things is the sum of the mobility of electrons and holes. If you think we have free electron hole pairs, and the mobility is the velocity per unit field strength of a charge carrier, the ease with which you can move it. And then there is, of course, the density of absorbed photons, but then times the yield of charges, if you look at the real mobility due to charges, divided by the total density of particles that you make, and the number of charges plus the number of excitons. So this is a quantum yield times the original density that gives you the real density of the charges. And the same for the imaginary component of the conductivity. So you have an out-of-phase motion of charges, out of phase with the fields. So there you get again something with the imaginary component of the mobility, the quantum yield of the charges, so the number of charges divided by the number of charges in excitons, and then an imaginary mobility due to the polarizability of excitons. So the polarizability determines the dipole moment induced by an electric field. And so the dipole moment induced is alpha times the electric field strength. That gives you let's say a phase delay, an imaginary conductivity, and that is proportional to the number of excitons you have and the fraction of excitons. Now we excited our nanoplatelets to begin with 6 electron hole pairs in this case, and we looked at the terahertz conductivity. In the upper panel there's the real terahertz conductivity, that let's say due to the charges. In the lower there is the imaginary terahertz conductivity due to the out-of-phase motion of charges and the polarizability of excitons. Now here you see a little bit of a noisy curve, and that is just simply the noise level of our terahertz setup, and then we increased the number of absorbed photons per nanoplatelets to on average 53. And what you see now here is really conductivity as a function of time in picoseconds. The real conductivity due to charges has increased a little bit, but not so much. You could say maybe a factor 2. But the imaginary conductivity here has changed much more. So it has changed from there to there. I would say it's almost an order of magnitude. So if you would only have free charges, then let's say you have, if there were no excitons at all, then the real and the imaginary conductivity should scale in the same way with the number of absorbed photons. The fact that there is a difference immediately shows you that you have excitons, which is also found from all the other studies. So that is good.
When you do this, are you now doing just a one shot 53 excitons, or is it you?
We average. So we have a pump and a probe at a fixed delay, and we determine that delay by having the probe going over longer optical paths than the pump, and that we can vary. We can just move a mirror automatically, and then for each pump probe delay, we average over thousands of shots.
But it's not that you keep pumping and you measure with this terahertz. You do one pump and then you do the terahertz.
One probe,
so that you
and
know
then
that you're creating all of these excitons at the same time.
in one pump, yeah. So now we did again this photo bleaching experiment as I showed you before. So we make excitons and then we look at the exciton energy with our probe photons at the emission of photons. And if we do that, so these are the curves that we had before for the terahertz conductivity, the real component, and then the imaginary in blue and the imaginary in red. And now we look at the number of excitons by the stimulated emission. And then we were close to the same number of excitons in a nanoplatelet. And then you see for this optical bleach, where you really count for the excitons, that it follows the blue curve of the imaginary terahertz conductivity and also the red curve. So this sort of already gives you an experimental indication that you predominantly are producing excitons. So from this we concluded already excitons survive at a high density and we don't get an electron hole plasma. And to look at this further, we varied the pump intensity of our laser tools. So we went from the number of absorbed photons on average from 6 in steps shown here to 53. And then we averaged the terahertz conductivity signal for the real and the imaginary component between 6 and 10 picoseconds. And then we plotted that, so the terahertz conductivity, the imaginary and the real conductivity by these closed and open symbols as a function of the number of absorbed photons on average per nanoplatelet. And then you see that the real conductivity increases and then it's nearly constant. So we have some charges, but then the imaginary conductivity due to the excitons really increases. So you have way more excitons and you still have them at a high density. So from the exciton binding energy, we estimated a Bohr rate of 1.2 nanometers. So we should, if you take these sizes into account, completely fill up the nanosheet with 60 excitons, so about 60 photons absorbed. We went up to 53, so it's close to the 60. So as I said, you could have expected this transition to an electron hole plasma, but we didn't get it. Now, we had excitons, otherwise we wouldn't have had this large imaginary component. So the excitons are stable even at a high density. And now how to understand it. And that is where Henk and Francisco Garcia Flores, a former PhD student with Henk, helped us. So they worked out the equilibrium between the excitons and the free charges. The second order reaction of electrons and holes forming excitons that can be back converted into charges by thermal dissociation. So what they took into consideration is a Fermi-Dirac distribution for the electrons and for the holes. There's the effective mass of the electrons and holes against the potentials. For the excitons, the Bose-Einstein statistics. So the excitons have the total mass of the sum of the electron and the hole masses. And here is the chemical potential of the excitons minus the binding energy of the excitons. I'll get to that, how they obtain that. And they have, of course, the conservation of particle densities. The number of electrons and number of holes should be equal. That is the number of charges, and the number of photons absorbed must be equal to the number of charges plus the number of excitons, and there is an equilibrium between the chemical potentials. What we needed is the exciton binding energy, and the exciton binding energy is a function of the dielectric constant, and the dielectric constant is a function of the number of charges you have around you. So they took into account, this is, let's say, the Schrödinger equation for excitons, for 2D, it's like a hydrogen atom, 2D hydrogen atom equation, but now there is a screened potential, it's not just the bare Coulomb potential, and the screening depends on the number of charges, the density of charges in the nanosheets. And now, the screen, let's say, I don't know if this is incorrect, I'd like to hear it from you. The way I see it, the electron can move in between the electron and the hole and therefore reduce the attraction, or it's going to stick around the hole a little bit. And okay. So the screen potential was this expression. Maybe if you want to know more about it, let me know, or we discuss it afterwards. But I think Henk is the expert. And what we now found is that the screening length, there's a screening length in this potential that you can see here, here, and here. So the screening length, which depends on the density of charges, causes the screened Coulomb potential to depend on the density of charges. And they calculated the screening length, let's say the distance at which the Coulomb potential falls off. Then the screening length decreases, it's shown here as a function of the density of charges, it falls off. Because if you have more charges, the earlier when you are away from the counter charge, you don't see the counter charge anymore, and it becomes constant in 2D at a high density. For 3D, it really goes to 0. And as a consequence, if you calculate the exciton binding energy here, versus the average number of charges in a nanosheet, because the screening becomes more and more important, the exciton binding energy becomes less, and because and it goes from this value very negative to minus 45 millielectron volts, and that's where it saturates, and it saturates because the screening length becomes constant. So at higher and higher density, the Coulomb potential becomes the same, independent of the density. So it should be become constant, and interestingly, they calculated it to be minus 45 millielectron volt, and that is greater than thermal energy kT at room temperature, which is 25 millielectron volt. If it had been less, then the excitons would simply dissociate thermally, but this is a little bit larger, almost twice as large, so that keeps the excitons are still bound. So they calculated, let's say, the real and imaginary conductivity, the expressions I've shown you before, and they have been taken into account the electron and the hole equilibrium. Then you have still two unknowns to calculate conductivity, that is for the excitons, the polarizability. Now there is an analytical expression for the 2D exciton polarizability, so that's a squeezed hydrogen atom, let's say, but then with a reduced mass of the exciton, so it has the effective masses of the electron and the hole in it. And then we treated the mobilities of the charges as fitting parameters. And in these fits, there is in fact a diffusion coefficient, and you can calculate the effects of the finite sizes of the lateral, the finite lateral dimensions of the nanosheets. And so there is the diffusion constant or the DC mobility, and the finite lateral sizes then give you an AC mobility that depends on the DC mobility and on the sizes. Now that was all taken into account. Then the theoretical model is shown here with the dashed line for the real conductivity due to the charges. Now I think it completely coincides with the experimental data to within the experimental uncertainty, and the same holds for the imaginary component. And from these calculations, it turned out that the quantum yield of charges is way less than the quantum yield of excitons. I've forgotten the precise numbers, but it was less than 10% charges. And the fitted DC mobilities that were used in the theoretical model are very close to the bulk values. So the fit gave 527 centimeters squared per volt second For electrons, and it's in bulk, there are also old data, 600 is somewhere in a handbook, and for the holes it was surprisingly close to the experimental bulk value of 40. We didn't put it in, we came out of the fit. So I think the theoretical model has really explained and further corroborated the experimental observations where we could only qualitatively infer some conclusions that we had excitons, but now it has really been corroborated by theory. So the overall conclusions. First of all, we think that excitons move coherently like a particle in a box along in the lateral directions of these nanosheets. The photo-generated excitons, electrons, and holes equilibrate in about a picosecond, and probe photons can produce bi-exciton strions or induce emission of photons from excitons. At a high density, when you fill up, let's say, the whole nanosheets with excitons that are touching each other, you still have excitons and don't get an electron hole plasma. Now, the fact that these excitons move so easily is good for photovoltaics, because in photovoltaics you want to produce, let's say, an exciton somewhere, but you want to dissociate it in free charges, so it should move somewhere to another material component where the electron and hole can separate, let's say at the p-n junction. And the fact that the excitons are still stable at a high density is very good if you want to make lasers or LEDs that operate at a high density, because they get many excitons close together and you want them to stay bound. Okay, then the acknowledgements. In my group, postdoc mediator for Ida and Aditya Kulkarni, a former PhD student, did all the experiments on the optical and terahertz spectroscopy. We got samples made by Bas Saltzman, a former PhD student with Daniel. The last part about the electron hole parts was done with samples we got from Peter Geigerhout and Siebbeles, and it was a long time ago. And then the theory was done by Francisco Garcia Flores, who was a PhD student with Henk. And I want to thank you for your attention, and everything was funded by NWO. Should also
Okay, there were already quite some questions, so thank you very much. Maybe there's some more questions. Yeah.
Quick one. So if you now are making as many excitons as you can in these nanoplatelets, what then happens if you go to, I guess, would it be stronger pump pulses, longer? Do they saturate? Do you basically see that nothing more happens if you try to put even more excitons in there?
I think you can put more and more because, well, to some extent they are bosons, but they are not real bosons, they are quasi-bosons. So at some point, well, first of all, you may get electrons because we didn't take into account any screening due to exciton-exciton interactions, and they are going to become important. But then I would say that always the second exciton that you make after the first exciton is different from the first one, because you have taken already k-states from the valence and conduction bands to make the first excitons, so you have less available for the next exciton. So I can imagine that at some point you can't make more, because you after relaxation, if you go deeper, if you make more energetic excitons, yes, because there are always k-states going deeper and k-states going up. But if you want to produce them near the band gap, at some point it becomes more and more, you make probably more energetic excitons, but not this, they are going to differ more and more from the first one. I think there is a lady called Condosco or something in Paris who calls this the moth-eaten effect. So the moth eats up the electrons.
Yes?
Yeah. Thank you for the presentation. I have a couple of questions. The first one being, did you check the state of the nanoplatelets after creating this 53
Yes.
excitons per nanoplatelet?
Yeah, I always ask my PhD students, start with a low fluence, low intensity, measure everything, go up, and if you go up, go back, because once you go back and it's different, you can stop. You have destroyed your sample. So we always go back to the lowest frequency, or the lowest intensity we begin with, and we look at the steady state spectra, PL spectra, after the experiments.
It's surprising that they stay.
Yeah.
And then I was wondering about the slide 20 at the first part. presentation. If the model you presented could also explain the Stokes shift observed between the PL and the
Yeah, it's a good
absorption.
question.
Because in some measurements, it almost looks like it disappears, and you also have the contribution of the other bands, but I wonder if it accounts for that.
Very good question. You would think, if you look, it's a Stokes shift, and with the Stokes shift, I think you mean that if you produce an exciton, it relaxes the nuclear lattice and it gets a lower energy. And that is the normal Stokes shift in fluorescence. Here it's not the case. The Stokes shift was 0. We didn't, in the model we had no Stokes shift. It is in fact a blue shift of the absorption. This absorption is more blue shifted with respect to the PL because the absorption is due to transitions to the lowest exciton levels, plus a little bit to the next exciton level and the higher levels, but it's mainly the second exciton level that causes the absorption to blue shift a little bit. With respect to the photo emission, the PL, which is predominantly from the lowest exciton state.
Yeah.
And if you now make it wider, then the next exciton energy level, to which you also excite in the absorption, lies at the lower energy, because the box gets wider,
yeah.
And the blue shift of the absorption is a tiny bit less.
Thanks.
There was, yeah.
In these nanoplatelets where you said you indeed do not find an electron hole plasma, but the excitons they remain stable. Will it be possible to achieve Bose-Einstein condensation of the excitons if they are still, I don't know to what extent they are still behaving as bosons?
If they behave like bosons, I would say you should be able to get the Bose-Einstein condensation, also thanks to the fact that they remain stable. I don't know about it, it are quasi-bosons, it are not real bosons, and so the Bose-Einstein condensation, I would say, is different from if you have real bosons. And to what extent it differs is an interesting thing to investigate, and I can't oversee that. There is, the only thing that I know is that there is a so-called deviation operator. So for you are the theoretician, for bosons you have a commutator that is a delta function, and there is something extra if you have excitons. And I think it would be very interesting to see what this deviation operator, again, Condes code is maybe.
And then if you have the idea of checking that experimentally, or does it require?
I think that the properties of the multi-exciton state at low temperature will be affected by that state. So that operator is present. So I think other properties should depend on that. But what properties, how, that I don't see yet how, but I'd like to discuss it with you, how we can get insight in the importance of that next term.
So just in the literature, not on this type of quantum wells, so to say, but on more professional quantum wells, single quantum wells made by solid state chemistry. There's a cadmium telluride paper of Kasperzak et al. In, I think, 2012, which saw in cadmium telluride Bose-Einstein condensation of excitons at 20 Kelvin, so not at very low temperatures, but at reasonable temperatures already. I have a small question, maybe.
Yeah.
So you certainly convinced us that you keep excitonic particles at, even at room temperature at very high densities instead of free carriers, but you also showed with the probe measurements that if you have a probe, you can form bi-exciton states and trial states, but you don't seem to take this into account for your explanation once you have many excitons. So why don't you get bi-excitons? And there is also a paper of Seher that showed that the lasing is mostly due to bi-exciton to exciton transitions. Would that affect your theory or not?
That was the next paper by Henk and Francisco where they took into account the effect of bi-excitons, and for the densite.
I don't know this paper.
I can show a graph from that paper that the number of there are bi-excitons at a high density, but the number is not so large. So it could, let's say, neglect it. Here it is. Here's one. This is the fraction of bi-excitons as a function of temperature and photoexcitation density. This horizontal line is room temperature, And these dots are the lowest and highest exciton densities in our experiment. So you can see that here it's light blue, is 1. So here the yield of bi-excitons is 1. But in black is, let's say, excitons only. So you see that at the highest densities, now this is per Bohr radius squared, but let's say it gets a little bit purple. So there are some bi-excitons. So my conclusion would be, since without taking into account this fraction of bi-excitons, we could already explain the data. So if you would take it into account, it shouldn't matter too much. And if I remember well, then, but Henk should correct me, is that the polarizability of bi-excitons was close to twice as much of an exciton. So it doesn't matter. So if you convert 2 excitons into a bi-excitons, you would hardly see it in the terahertz conductivity experiments because the polarizability is the same.
But then the fact that Zeger has to assume that the lasing is the XX to X transition is due to the fact that you only get population inversion if you assume this? Well, he sees it also in the energy, I think, because...
Yeah, he sees it in the energy, and that's the bi-exciton energy. So you can see it in photoluminescence or stimulated if you have So if you would have looked,
it's only the bi-exciton that can...
The emission from the bi-exciton is redshifted from the exciton, that you can observe. Yeah. But in the terahertz conductivity experiment, you measure the polarizability, that is not really changing much, so you cannot observe it with terahertz.
But the reason that you see only, let's say, the expected XX to X lasing transition is due to the fact that there is absence of reabsorption. So that's their theory. Although you have mostly many other type of particles, you have enormous amount of normal excitons.
Yes, I would say so, yeah. And if then you do your lasing experiment at bi-exciton resonance, then you see that and you are blind, let's say, in their experiment for the excitons, single excitons.
Okay, self-solving last question.
Yeah, it was not clear to me why you expected a transition from several excitons to a plasma. Because that would imply that as you become harder and harder and harder, you would be changing the interaction between electron and hole, so that at a certain pumping power, at a certain density of excitons, that interaction would become very weak, so that there's no dissociation. I don't see how that would have an infinity is always the same. Right? I didn't get your argument for the expectation that you would eventually see a transition to electron hole plasma.
Well, if all the excitons, let's say, spatially overlap, and let's say if I have one exciton here and one exciton there, then this electron is bound to this hole and that electron to that hole. And
yeah, but I think, that's what I didn't get, because I would expect that if you have so many excitons that they start spatially overlapping, that would have the consequence of increasing the binding between them.
Yeah, the total energy, yeah, okay, the total energy, let's say if you see it like like forming a molecule, if I have 2 hydrogen atoms, if they get close together and form an H2 molecule, the total energy goes down, because each electron now fills 2 nuclei and so, and they have to pay for the electron repulsion, so the total energy goes down, but the electrons in that system, they don't know to which nucleus they belong anymore. Now you cannot say one electron belongs to the left proton and the other to the right proton, because now they are in a molecular orbital.
Yeah, you would lose the correlation between the electron hole.
Exactly.
Right?
And
But I think that would be more likely to see if you go to material with say a lot more covalent character, like if you look at the lead selenide nanoplatelets, for instance.
If you work in 3 dimensions, yeah, if it's a 3-dimensional system, then the screening length goes to 0 if the density increases to infinity, yeah?
Yeah, in 3 dimensions. But
and so you
screen, how you would get
well, if the screening length goes to 0, it means you have no binding anymore. So in 3 dimensions, you always go to particle plasma. Yeah? But somehow the observation we made is that in 2 dimensions, the screening length saturates. So you always have still a Coulomb potential. So the exciton is much more stable in 2 dimensions than in 3 dimensions. That's the main observation, that the screening length doesn't go to 0 if you increase the density. It actually saturates. And that comes because the density of states is constant in 2 dimensions. Yeah, whereas in 3 dimensions it goes with the square root.
Yeah.
Because you have the screening length has to do with the density of states at the Fermi element.
What thickness does it break down? Is 5.4 or like the 2D scenario? When does it get to the 3D scenario? And what exact thickness is it? 5.4?
Yeah, I would say, yeah, if it's more, yeah.
But yeah, this argument that I'm using has nothing to do with 2 or 3. It doesn't change it as a function of density. You do not go to a 3-dimensional situation. Because the electron wave functions are always localized in or they're always squeezed in the 3rd direction. So.
Then one more conclusion would be that the heat transport is extremely fast. Because when you reach the limit of having 60 excitons in the nanoplatelet, by that time you should already have deposited so much excess heat from the relaxation, from pumping.
From above the,
Because you were exciting way above the.
Yeah, that we calculated, it's about 4 Kelvin. It's not so much. So if you take specific heat, we just did it for another material, MOS2, and if you are, let's say, 1 eV above the band gap, there are even 2 eV above the band gap. For MOS2 it was, we did it 2 weeks ago or so, it's 4 Kelvin. I did it many times because it's always the question you get with pumped probe lasers. So it's 4 Kelvin, but that's not the only story, because you could say, okay, for 1 pulse it's 4 Kelvin, but we are giving thousands of pulses with 4 kilohertz. So between, let's say, a tenth of a millisecond or a quarter of a millisecond, if you work at 4 kilohertz, it should have dissipated its energy again, because it should cool down, and because 100 times 4 Kelvin is already 400 Kelvin extra, and the heat dissipation, if you calculate that, is sufficient in common materials. Otherwise, you could never do pumped probe laser spectroscopy. You would simply blow up everything. So per pulse, unfortunately, it's only a few Kelvin, and the heat dissipation in all the materials I have encountered so far is sufficiently fast that you release the heat before the next pulse arrives.
Okay, I think we're running out of time, so let's thank you again.